Look at your hands, hold them up in front of you, palms facing you. They are mirror images of each other. Your left thumb is on the left, your right thumb is on the right. You can't lay your left hand perfectly on top of your right hand so that they match. The thumbs and fingers will point in opposite directions. They are fundamentally different. This property is called chirality or just handedness. It's a basic feature of our three-dimensional world. Now imagine a universe that is a perfect mirror image of ours. Every person, every planet, every galaxy is flipped. Your heart would be on the right side of your chest. The letters on this page would be backward. A screw that you turn clockwise to tighten our universe would need to be turned counterclockwise in the mirror universe. It seems like a perfectly plausible place. For a very long time, physicists believed that the fundamental laws of nature wouldn't care about this difference. They thought that if you ran an experiment and then ran its perfect mirror image, you would get a perfectly mirrored result. The rules would be the same. This idea was called the conservation of parity. It was a core belief, a deeply held intuition about how the world should work. It felt elegant and symmetrical, and it made sense. Why would the universe have a preferred direction? Why would it be left-handed or right-handed? It turns out that it does. The universe is, in a very deep and strange way, left-handed. The mirror is broken. The laws of physics are not the same in the mirror image. This discovery was one of the great shocks of 20th century physics. It completely upended our understanding of reality and pointed toward even deeper mysteries, including the very reason we exist at all. For decades, the idea of parity conservation was rock solid. It worked perfectly for gravity. It worked for electromagnetism. It worked for the strong nuclear force, the one that holds atomic nuclei together. In all the realms physicists could test, the universe seemed ambidextrous. It treated left and right with perfect equality. A particle spinning to the left behaved just like its mirror image spinning to the right. No experiment had ever shown otherwise. It was so reliable that it was used as a tool to rule out certain theories or predict the outcomes of experiments. It was a law. But in the early 1950s, a strange puzzle emerged in the world of particle physics. Physicists were discovering a whole zoo of new, exotic particles in their accelerators. Two of these particles were causing a lot of confusion. They were called the tau meson and the theta meson. On paper, they looked identical. They had the same mass, the same electric charge, the same lifetime. By all measures, they should have been the same particle. But they had one bizarre difference. They decayed into other particles in different ways. The theta particle decayed into two particles called pions. The tau particle decayed into three pions. This might not sound like a big deal, but it was a huge problem. According to the rules of parity, a particle could decay into two pions, or it could decay into three pions, but it couldn't do both. Here, the two-pion decay had one kind of parity, and the three-pion decay had the opposite. So, if the tau and theta were the same particle, it meant this particle was violating the sacred law of parity conservation. It was like a person who was simultaneously left-handed and right-handed in a way that should be impossible. Most physicists thought there must be some mistake. Maybe they weren't really the same particle. Maybe our measurements of their mass were just slightly off. The conservation of parity was too important to just throw away. But two young theoretical physicists, Sungdao Lee and Chen-Ning Yang, took a different approach. They were brave enough to ask a radical question. What if the tau and theta really are the same particle? And what if the law of parity conservation isn't a law at all? They went back and looked at the evidence. They discovered something astonishing. While parity had been confirmed again and again in experiments involving the strong force and electromagnetism, no one had ever actually tested it for the weak nuclear force. The weak force is one of the four fundamental forces of nature. It's much weaker than the strong force or electromagnetism, which is why it's harder to study. But it's responsible for certain kinds of radioactive decay, like the beta decay that happens in atomic nuclei. The tau-theta decay was governed by this weak force. Li and Yang realized that everyone had just assumed that parity was conserved by the weak force because it was conserved by the other. It was an assumption masquerading as a fact. In 1956, they published a paper suggesting that parity might not be conserved in weak interactions. They proposed a series of experiments that could test the idea directly. It was a bold and speculative paper. It was questioning a foundation of physics, but it laid out a clear path to find the answer. The world of physics was skeptical, but intrigued. All they needed was a brilliant experimentalist to carry out the test. That experimentalist was Qian Wu. She was one of the most respected physicists of her time, an expert in the meticulous and difficult work of studying beta decay. Li and Yang went to her and asked for her help. She understood the importance of the question immediately. She dropped her other plans and set to work on what would become one of the most famous experiments in modern physics. The experiment she designed was ingenious, but incredibly difficult. The idea was to look at the decay of a radioactive element and see if it showed a preference for a certain direction. The key was to get a bunch of atomic nuclei all lined up, pointing in the same direction, and then watch where the electrons from their decay flew off. If parity was conserved, the electrons should fly off equally in all directions. There should be no preference for up or down relative to the alignment of the nuclei. The universe shouldn't care which way the nuclei are pointing. A mirror image of the experiment, where the nuclei were pointing the other way, should produce a mirror image result. To line up the nuclei, Wu needed two things: a very strong magnetic field and an incredibly low temperature. She used an isotope called cobalt-60. The nuclei of cobalt-60 atoms have a property called spin, which is like a tiny internal magnet. A magnetic field can align these tiny magnets, but at normal temperatures, the atoms are all jiggling around so much that any alignment is immediately lost. You have to cool them down to stop the jiggling, and Wu had to cool them down to a temperature of just 0.01 degrees above absolute zero, the coldest possible temperature in the universe. This was an extreme technical challenge. She collaborated with a team at the National Bureau of Standards that specialized in low-temperature physics. They set up the experiment, they cooled the cobalt-60, they applied the magnetic field. The nuclei dutifully lined up. Then, the cobalt-60 atoms began to decay, spitting out electrons. Wu and her team watched the detectors, and they saw it. The result was not random. It was not symmetrical. Most of the electrons were being emitted in one direction, specifically in the direction opposite to the spin of the cobalt-60 nuclei. It was a stunning, world-changing result. The universe did have a preference. If you looked at this experiment in a mirror, it would look different. In the mirror world, the nuclei would be spinning the other way, but the electrons would still be flying out in the same direction relative to the lab. The mirror image experiment gave a different result. Parity was not conserved. The weak force was fundamentally asymmetrical. The universe at its core could tell the difference between left and right. When the results were certain, Li and Yang were informed. The physics community was in shock. It was as if someone had proven that the value of P was different on Tuesdays. A fundamental symmetry, a beautiful and simple idea about the nature of reality, was gone. Li and Yang won the Nobel Prize in Physics for their theoretical work just a year later in 1957. Many felt that Wu was unfairly overlooked for the prize, as it was her brilliant and difficult experiment that provided the proof. So what does it actually mean for the universe to be left-handed? It's not about the shape of galaxies or the direction planets spin. The handedness is written into the very nature of fundamental particles. Many particles, like electrons, have a property called spin. You can think of it like the particle is a tiny spinning top. It can spin clockwise or counterclockwise. Now imagine the particle is also moving forward. If the particle is spinning in a way that's opposite to its direction of motion, physicists call it left-handed. Think of a left-handed screw or a corkscrew. As you turn it left, it moves forward. If the particle is spinning in the same direction as its motion, it's called right-handed. What Wu's experiment and subsequent ones showed is that the weak nuclear force is incredibly picky. It almost exclusively interacts with left-handed particles. It's like the weak force is a gatekeeper that only lets left-handed particles through the door. It mostly ignores right-handed particles. It's not a small effect, it's a maximum violation. The weak force is as biased as it could possibly be. The most extreme example of this is a particle called the neutrino. Neutrinos are tiny, almost massless particles that are produced in nuclear reactions, like in the sun. It turns out that every neutrino ever observed is left-handed. Every single one. Their mirror images, right-handed neutrinos, have never been seen. It's as if they don't exist, or if they do, they don't interact with our world in any way we can detect. Similarly, every anti-neutrino ever observed is right-handed. The weak force separates the world and the anti-world into opposite-handedness. This isn't just a slight preference, it's a fundamental rule of the universe as we know it. This discovery of parity violation raised an immediate question. What about the other forces? As physicists looked closer, the old results held up. Gravity doesn't care about handedness. Electromagnetism doesn't care. The strong force doesn't care. They all respect parity symmetry. Only the weak force is broken. This makes the weak force seem very strange, the odd one out among the four fundamental interactions. It's like having a set of perfectly symmetrical building blocks, but one of them is lopsided. Why would nature be so elegant and symmetrical in three ways and so bizarrely asymmetrical in one? This remains one of the deep, unanswered questions in physics. After the initial shock of parity violation, physicists tried to salvage some kind of symmetry. They thought, okay, maybe the mirror image of our universe isn't the same, but what if we not only flip it in a mirror, but also swap all the particles with their antiparticles? An antiparticle has the same mass as its regular particle counterpart, but the opposite electric charge. An electron is negative, its antiparticle, the positron, is positive. Maybe this combined operation called CP symmetry charge parity would hold true. The idea was that a left-handed electron in our universe would behave exactly the same as a right-handed positron in the mirror universe. The laws of physics would be restored if you flip both charge and parity together. This seemed like a neat fix. The universe wasn't just left-right symmetric, it was something more complex. For a while, it seemed to work. CP symmetry seemed to be a valid law of nature. But then, in 1964, another bombshell dropped. An experiment by James Cronin and Val Fitch showed that even this combined CP symmetry was violated. They were studying the decay of particles called neutral kaons. They found that on very rare occasions, these particles decayed in a way that was forbidden by CP symmetry. The violation was tiny, not maximal like the parity violation of the weak force, but it was unmistakably there. The universe wasn't even symmetric if you flipped both the mirror and the charge. This discovery was another shock, and it earned Cronin and Fitch their own Nobel Prize. So now two fundamental symmetries had fallen. First parity P, then the combination of charge and parity CP. There is one last great bastion of symmetry that physicists believe holds true. It's called CPT symmetry. This says that if you flip the charge C, flip the parity P, and also reverse the direction of time T, then the laws of physics must remain the same. A left-handed electron moving forward in time in our universe should behave exactly like a right-handed positron moving backward in time in a mirror universe. This CPT symmetry is much more fundamental than P or CP on their own. It is deeply woven into the fabric of our current understanding of physics, into quantum field theory and Einstein's theory of relativity. If CPT symmetry were ever found to be violated, it wouldn't just be a surprise, it would mean that our entire framework for understanding the universe is profoundly wrong. So far, every experiment has shown that CPT symmetry holds perfectly. It seems to be the one mirror that isn't broken. This might all sound like an abstract game that particle physicists play in their labs. But the consequences of these broken symmetries are immense. The fact that CP symmetry is violated, even by a tiny amount, might be the single most important reason why we exist. It could be the answer to one of the biggest mysteries of all: why is there something rather than nothing? According to the Big Bang Theory, the early universe was a searingly hot soup of energy. As this energy cooled, it should have created particles and antiparticles in exactly equal amounts. For every electron, there was a positron. For every quark, an antiquark. The problem is that when a particle meets its antiparticle, they annihilate each other in a flash of energy. So, if they were created in perfect balance, they should have all found a partner and annihilated, leaving behind a universe filled with nothing but light. There would be no matter. No galaxies, no stars, no planets, and no people. But that's not what we see. We live in a universe made almost entirely of matter. There is very little antimatter around. Something must have happened in the first moments of creation to tip the scales, to create a slight excess of matter over antimatter. For every billion antiparticles, there must have been 1,000,000,001 particles. All the antiparticles annihilated with their matter partners, and that one in a billion left over is what makes up everything we see today. In 1967, the Soviet physicist Andrei Sakharov laid out the conditions necessary for this imbalance to occur. One of those crucial conditions is the violation of CP symmetry. The laws of physics must treat matter and antimatter differently. The tiny asymmetry that Cronin and Fitch discovered in the decay of kaons was the first experimental evidence that such a difference existed. The universe's fundamental handedness, its preference for left-handed particles in weak interactions, and the subtle ways it violates the combined charge parity mirror, is our best explanation for why the matter in the universe survived. Our existence is seemingly a leftover, a cosmic rounding error made possible by a flaw in the universe's symmetry. The story gets even more fascinating. The universe's preference for left-handedness at the subatomic level may have an echo in life itself. All life on Earth is also fundamentally handed. The building blocks of proteins are amino acids. There are left-handed and right-handed versions of most amino acids, just like your hands. But in virtually all living things, from the simplest bacteria to human beings, the proteins are made exclusively from left-handed amino acids. Right-handed amino acids exist, but life doesn't use them. Similarly, the sugar molecules that make up DNA and RNA are all right-handed. The mirror image versions, left-handed sugars, are not used. This property is called homochirality, and it's a deep puzzle. Why did life choose one hand over the other? If you synthesize amino acids in a lab without any special guidance, you get a perfect 50-50 mix of left and right-handed versions. So, why is life so one-sided? One speculative but compelling theory ties this biological handedness directly to the fundamental handedness of the universe. The idea goes something like this. The early Earth was bombarded by asteroids and comets, which carried organic molecules, including amino acids, from space. These molecules in space were exposed to radiation, including the electrons from radioactive decay. As we know from Wu's experiment, the beta decay that produces these electrons is a weak force interaction, and it is parity violating. The electrons that are emitted have a certain spin, a certain handedness. The theory suggests that this naturally polarized radiation might have preferentially destroyed one type of amino acid over the other. Over millions of years, this could have created a slight excess of left-handed amino acids in the cosmic dust that eventually seeded life on Earth. When life got started, it simply used the building blocks that were most abundant. It chose the left-handed amino acids because there were more of them around. Once that choice was made, it became locked into the genetic code and passed down through all of evolution. This is still a hypothesis, and it's very difficult to prove. But scientists have found slight excesses of left-handed amino acids in meteorites that have fallen to Earth, which lends some support to the idea. It's a mind-bending thought. The same subatomic quirk that explains why our universe is full of matter might also explain why our bodies are built the way they are. The asymmetry of the cosmos might be written into our very cells. So, where does this leave us today? We know the universe violates parity. We know it violates CP symmetry. We know these violations are not just curiosities, they are essential to our existence. But we still don't know why. The current theory of particle physics, known as the Standard Model, is incredibly successful. It describes all the known particles and forces except gravity with stunning accuracy. But it doesn't explain the universe's handedness. The theory simply accepts it as a fact of nature. The asymmetry is written into the equations by hand, as an observed parameter, not as something that emerges from a deeper principle. This is a huge sign that the Standard Model is incomplete. There must be a bigger, more fundamental theory out there that explains where this asymmetry comes from. Why is the weak force so different from the others? Are there right-handed neutrinos, and if so, where are they? Maybe they are extremely heavy and decayed away long ago. Maybe they interact through some new, undiscovered force. Finding the answers to these questions is one of the biggest goals of modern particle physics, driving experiments at places like the Large Hadron Collider. The discovery that the universe is left-handed was a lesson in humility. It taught us that our intuitions about how the world should be, our love for elegance and perfect symmetry, can be misleading. The universe is under no obligation to conform to our aesthetic preferences. Reality is often stranger, messier, and more interesting than we imagine. It all started with a simple question about a mirror. If you looked at your reflection, would the world you see behave by the same rules as your own? And for centuries, the answer was assumed to be yes. It was a beautiful idea. But science isn't about what we want to be true, it's about what we can test. And when Qianxin Wu and her team watched those electrons from decaying cobalt, they saw the truth. The reflection in the mirror is a stranger. It's a different place governed by slightly different laws. Our universe has a preference. It has a bias written into its very core. And in that imperfection, in that broken symmetry, lies the reason that we are here to wonder about it at all.